Dr. Shi is a professor of Department of Mechanical and Energy Engineering at University of North Texas. And Dr. Shi is a associate editor for Frontiers in Materials and served on the executive board of the Society of Wood Science and Technology. Thank you very much.
Thank you. Today, right? Where's the control? Yeah, thank you. Thank you for the introduction. And thank you for the invitation from the board. And I really enjoyed the meeting so far, and very good talks. And I'm looking forward to the next 2 days and for more exciting seminars. And so far, there's many talks talk about the wood treatment, and this is the wood conference. And treatment is very important, and steps to for building. Okay, and now I'm glad to present a new what we call it the self-flow lumber treatment technology, and we do have a patent on it. It's been authorized, and let me see here. So okay, and we have before that, that's over here. Okay, and we do have a company and try to commercialize this technology. Okay, and acknowledgement is my student Shen, and he graduated end of last year. He got his PhD degree, and he's now a postdoc working with me in my lab. Okay, and talk about the wood treatment. And we have a fire retardant treatment, then termite treatment, decay treatment, decay resistant, and this becomes a very important issues, especially last year, like the California fire, bring the attention. So if the building materials been, all the wood materials been treated, so reduce the damage significantly. And if we talk about treatment, it can be 2 different ways. One is we call the non-chemical treatment, like some steam and those type of treatment is try to improve the dimensional stability, etc. And another is the chemical treatment. So we're going to just talk about, emphasize on the chemical treatment here. And chemical treatment wood preservative, the traditional treatment, alkaline, it's the ACQ, borate, and the fire retardant treatment, and at least those chemicals. I think Dr. Zhu mentioned quite a bit of chemicals used for the treatment, like mainly it's the borate, borax, and boric acid, and ammonium sulfate and zinc borate. Next is the chemical treatment. Is mainly is the delignification. So this wood treatment industry is like you're talking about a $6 billion industry. It's a huge market out there. And I'm just a little bit more on this delignification process, because this self-flow treatment process really works well on this delignification. I'm going to show you some of the data, and those are the list of the chemicals typically used for the delignification. Okay, and applications, and we have here about enough, a lot of those applications for the wood treatment, like a fireproof, like all the railroad tie and outdoor, and those wood products all requires treatment. Like the transparent wood, densified wood, insole wood, has been a lot of technology developed, especially in Bing's lab, and has been working on this. And those are all required delignification. Okay. Traditional treatment mainly rely on the pressure vacuum. Like and also there's some simple treatment process like immersion, and there's also SAP displacement and Buckley process. One has a pressure, one doesn't have a pressure. So, and those are the traditional treatment. We're going to in this slide, so we're going to compare different treatment technique and see what is the pro and the cons of each. Okay, and the limitations on this treatment. We categorized the treatment into two. Okay, one is with the pressure, one is without pressure. Okay, if there's no pressure, the treatment is pretty mild, but it's not uniform penetration, and treatment process is slow. With the pressure, and there's a potential has a damage of the wood integrity and the low efficiency. So, but the uneven treatment, the uniformity of the treatment is the key. And you can see on this pointer here. So you can see there's some damages and some pictures. If you do the pressure, introduce the pressure into the treatment. Okay, now self-flow. So this is what we're doing in this technology. It's inspired by the tree growth, and in the tree growth, there's from the photosynthesis on top. Oh, sorry. Okay. On top of the photosynthesis, then draw the water and go from the soil and go up. So through the capillary rise and also the pressure differences. Okay. And just to follow this mechanism, because the wood is a porous structure over here, and we just needs to do something on the top. Okay, simulate the photosynthesis process and to draw the liquid from the bottom up. So then we place the lumbers vertically in the tank. So here is let me see if I can. How can I? Is that on the way to the video? Yeah. How can I? Where's the mouse? If I can. Huh? Okay. Can you click that link? Oh, okay. Thank you. So that is the link. That is the link to my company, and there's a technology, and there's one demonstrated the process. Oh, what is that? Yeah. Oh, it's okay. If not, you can see this. So basically, I just want to see. It's a simulation, animation, demonstrate the process. Just two tanks. One is the treatment tank, and that is the treatment tank. This is the chemical tank, and this is the storage tank. So during the treatment, the process is from the bottom all the way up, and there's so I'm gonna show the figure how to set it up. Okay, there's a height differences over here. This is the lumber. This is lumber, and there's a little differences between. This is the absorbent sheet. So this is very important because that is the one who draw the liquid up, and there's some distance, and also the height from here to here. It's very important because that will control the process, the treatment rate. So this is what I try to demonstrate through the that video. Okay. Okay, and this is the one of the results in terms of the lignin content. So this process is very effective on the delignification. Okay, and we did the comparison. One is the first one. Okay, this result, and this is the It's an immersion process. Immersion process is without any pressure. Okay. And then after the immersion process treatment, we measure the lignin content of the treated lumber. And this is the results. Okay, so you can see on the edge, very low lignin content is below 5%. Okay, over here. Okay, but in the core, still lignin content is still very high. So that is the immersion process. And the second one, and this is with pressure. You can see the pressure does help with the delignification. And see that even in the core, there's a still reduction of the lignin content. So you can see this is red, is the original lignin content. And this is the lignin content after treatment. And this is our process. This is our process. This is the original lignin content. After our cell flow treatment, the lignin content is significantly decreased. This is about it's below 5%. It's below 5%. Okay, and very important is that we calculated the standard deviation. The standard deviation for the treatment, the lignin content is only 0.9 versus the others it's over 7%, 7 to 8%. So the traditional chemical treatment, the variation is very high. But with this cell flow treatment, the variations are very low, significantly lower than the traditional process. And if you look at the speed, okay, the delignification speed, and it is related to the size of the samples. And for the 2 by 2 by 2, the reduction is 2. The reduction. This is a cell flow process. This is the immersion process, and this is the vacuum. Okay, but our process, the reduction is 2 times faster. But for the bigger sample, 5 by 5 by 5, this is all small. But imagine if it is for the commercialization, it's a bigger specimen. The reduction rate is even higher, and this is 6 times quicker. Okay, so that is the comparison between compared to the traditional process. If you look at this SEM, okay, and this is the first one is the A, B, C is the delignified wood from the cell flow treatment. Okay, and the D, E, F is immersion process. This is a cell flow, this is an immersion, and this is a vacuum. Okay, if you look at the SEM, you can see there's after the cell flow treatment, there's a lot of voids opened. Okay, you can see very clearly here. But for the immersion process, still a lot of lignins in it, so the efficiency is a lot lower. Okay. And for the vacuum treatment, in addition to some of the cells still lignin in it, but you can see some cracks over here because of you apply the vacuum, apply the pressure, so that hurt the structural integrity of the wood. So that is one of the drawback for the pressure treatment process. Okay, and this is the performance of the lignification from different species. And we know the different species, the treatability and the permeability are all different. And this is the same thing happens to this cell flow. And for those species like basswood, for basswood, balsa wood, poplar, they're very effective. If you look at this, we compare. This is a cell flow. The second one is a vacuum, and this is a sap displacement treatment. This one is the simple immersion process, And this is the battery process. Battery process is similar to the set flow, but with pressure. Okay, and this is the comparison of this treatment. And we can see the cell flow process has significant lower lignin content. So after the treatment, this is the we measure the lignin content to check the treatment efficiency. Okay, from different methods, and this cell flow method has significant lower lignin content for these three species. Okay, you can see the efficiency, and also the impregnation depth. This is performance is very good. Okay, so this is for these three species, but for the pine, it's okay. For pine, it's okay. Okay, so still, but becomes the 10%, lignin in it. But for eucalyptus, very difficult to treat. So this is a very difficult, permeability is very low, and then basically this untreatable. Even using the cell flow, it's not treatable. So there's still have some limitations for the cell flow, but we try to, right now we're working on to develop the process using the cell flow and try to deal with those species difficult to be treated. Okay, and that is the still have some limitations too. Okay, and we developed a model, and this model is based on the Pauli's law. This is the equation, Pauli's law, and there's a long derivations of the equations, and we end up with this model. And okay, here's the process. Okay, the two important parameters is one is this is the treatment. Okay, this is a treatment. You have to position the liquid level is very important. You can't get too high. You can't get too low. Okay, so that is the liquid level. The liquid level cannot be higher than the wood itself, the lens itself. Cannot. They should have some little distance, and distance what we call is a T5. Okay, and this is the T1 is the length of the wood, of the lumber. Okay, and the T2 is the height of the liquid. Okay, too. And also another one is T3. This is the height of the liquid in the collection tank, and the distance between T3 and the T3 and the T2, what we call is the T4. That distance is very important. Okay, then we're checking the effect of T4 and the T1. T1 is the length of the lumber. Okay, and the T4 is to control to demonstrate how you control the setup during the treatment. Okay, now we plug into the lumber and we did the test. This is a long test. It's a lot of data, but we put it in one slice. You can see just first one is related to the T. Let me see how can see here T4. Okay, first one is related to T4. Okay, so we can see the higher the greater the T4. You can see the T4. Let me go back. Here's the T4 over here. The distance. Oh, sorry. The distance between the liquid level of the two tanks. That's a T4. Okay. The higher the T4, the greater the T4, the greater the flow rate, and then there's a lower the treatment time. So that is what the T4 is controlling the treatment time. Here's the lumber height. Of course, the longer the lumber, the longer the treatment time. Also, the flowing rate is also slow. Okay, and this is the cross section. Cross section basically doesn't matter, just initially, just affect initially, but when a certain time, it level off. Okay, so I'm going to just go to the summary table. This is the comparison of a different treatment method. Okay, for the external pressure applied, and with external cell flow, no external pressure. Immersion, no external pressure. But for the pressure treatment and the Bochry treatment, they have a pressure. Okay, so that's a pressure. And continuous liquid flow, cell flow, yes, it has a continuous flow. Bochry has a continuous flow, but the other three methods doesn't. Okay, and wood structure integrity, cell flow, yes. Okay, and immersion, yes. And sap displacement, yes. Okay, and the delignification speed, cell flow is high. The others is all slow. Okay, and the impregnation here it says moderate, and some high, some low. We say moderate because we cannot it consider the different species. Some species is very effective, but for eucalyptus, those type of species are slow. Okay, and the process complexity for these cell flows very simple setup. So those are the comparisons among the different treatment methods. So this is my conclusion. Sorry, I think I'm taking a little bit more time.
Thank you very much, Professor Shi. We will have time for one quick question.
Yes.
I understand this is the Bochry process is not the lignification, but otherwise, what are the differences between your method that is all established to the Bochry process?
Yeah, I think the majority of the wood treatment method right now is the pressure treatment, right? I think the AWPA standard has established, has all the pressure treatment standard procedure and using the pressure to represent the quality of the treatment, right? But right now, the cell flow is totally changed. We don't use pressure. I think we need to, if this is go get into market, we have to establish a new standard. Okay, and this process is very simple. We don't need the pressure chamber because it's a cell flow, and we just set it up. Take time and set it up and let it run. But we need to set up correctly. So like a liquid level and the absorption sheet, everything set it up correctly. So then I can, you just come back and pick up, and then the delignification is very effective. So this is the differences from this method, between this method and the existing method.
So
yeah.
Can your process apply to the four-dimensional number?
Yeah. We're right now we're setting up to scale up and get 8 foot. And 8 foot, and that's why we have this model set it up. You can estimate how long will that take for the treatment of the full length. Yes.
Thank you very much.